All right, section 4.3, we're going to be taking a look at greatest common divisors and least common multiples. In particular, today we're going to at least hope to get through the greatest common divisor part of it, and then on Wednesday we'll come back and do the least common multiple part. Sound good? All right, so our leading idea is the following. Greatest common divisor and least common multiple show how numbers relate through shared factors and multiples, revealing harmony and order in God's design. Understanding these relationships helps us appreciate unity and diversity in math and around the world. Integrating faith with greatest common divisor and least common multiple inspires purposeful teaching that values interconnectedness and balance in both mathematics and life. Let's pray. Dear Heavenly Father, I thank you for an opportunity to be here today. I pray that you would be in our discussion and that components of what we have worked on today would resonate and would stick with us, and that those pieces that maybe don't would be accessible easily should we need them in the future. We pray that you would give me clarity in what I say and the students clarity and good questions to ask. In Jesus' name, amen. So we're going to start with greatest common divisor, also sometimes called a greatest common factor. So if you see abbreviated GCD or GCF, same thing. This is the greatest or biggest whole number that divides all numbers in your set. And keep in mind, because sometimes people get confused and think greatest means it's a big number. It is not a big number. That number itself needs to be smaller than the number you're working with. So it's generally speaking a small number, not a big number. It's just the biggest of the small ones. Okay? Does that make sense? It's the biggest of the small values. So these are all factors, and you're looking for the largest one. And then we've actually come across this phrase, this word before, but I've tried to avoid using it. I think I was successful this time around, relatively prime. Have you heard me say relatively prime? I don't think I said it. I was trying really careful not to say it. It came up in section 4.1. So do you remember when we were looking at divisibility of property of sixes? And at the very end of that very first day of class, when we were looking at 4.1, we created a list of the haves and the have-nots. Does that sound familiar? All of these have this property, all of these don't have this property. What's common in this set that's not in this set? And what we established was that the ability to take the number and just break it apart into two factors, like 6, only works when the numbers that we break it apart into have no factors in common, right? 6 is 2 and 3, it works. 8 was 2 and 4, it doesn't, because 2 and 4 have a factor in common. Well, when numbers have no factor in common except for 1, they are called relatively prime. That doesn't mean that either of the numbers themselves are prime numbers. It just means that when you factor them down, they have no common factors. Okay, so you have to have two numbers. It's a relationship description. Okay, it's a relationship between these two values, and they have nothing in common. So we had an example here for relatively prime. We'll put the number, I'll do actually two numbers that are not already prime so you can see that it'll work. Let's go with 9 and 25. 9 and 25, neither of them are prime, right? 9 divides by 3, 25 divides by 5. They're not prime numbers, but they are relatively prime to one another, right? When we compare them to each other, they share no common factors. These are relatively prime. Okay, so all right so far. Okay, so we're going to be taking a look at some different methods for finding greatest common divisors. There's going to be several of them. You're probably going to like one or two of them more than you like some of the other ones. There's value in each one of them. They sort of show a different perspective of what's going on. Some of them lend themselves better to like the math that students would have already done, like prerequisite math to where they are, which is really a very great thing. But maybe not so well to keeping going in algebra. And then some of them lend themselves really well to where the students are going in the algebra, but maybe not where they've been as much. So there's benefit and there's sort of like, negatives to all of them. The first one we're going to look at is called the intersection of sets method. In this method, what we do is we list all the divisors of each value. Notice it didn't say all prime ones. We're going to list all of them, all the divisors, and we simply find the largest divisor that they have in common. This method works really well with small numbers. You get really big numbers, it doesn't work so well because I don't want to list all of the factors of 4,625, right? Like that doesn't sound like a fun task. But if the number's small, it's not too bad. This one is one of those ones that lends themselves really well to where students have been because they've done divisibility and they've worked with that kind of concept recently enough in their history that this works really well with prior knowledge. So we're going to take a look at 12 and 15. Like I said, small numbers, and we're listing all the factors that they have. So we'll start with 12. So it always starts with 1. I'm going to go in order from least to greatest. So 1 will divide 12, and that would be 1 and 12. So sort of the ending, the first, they come in pairs. So if you wish, you could do it that way too. Let me do it that way. I kind of like that better. Let me do that. So 1 and 12, we'll stack them. What's going to divide 12 after 1? Next smallest number. 2, thank you so much. And it's 2 and 6, right? They come in pairs. What's the next number that will divide 12? 3. 3 and 4. And when we get to the 3 and the 4, we know we're done because there's nothing in between 3 and 4, right? So in some sense, if we sort of went around this direction, we would have them in order from least to greatest, and we didn't skip any because the 3 and the 4 were the biggest ones, and we were methodically going step by step as we went. Okay, let's do the same thing with 15. So 15, we start with 1, 1 and 15. What's the next smallest value that will divide 15? 3. 3 and 5. And then the only number between 3 and 5 is 4. Does 4 divide 15? No. So this is all of them, right? It's not a very long list. And we simply look at the two lists and we find the biggest number that's in both lists. And that number here is 3. It's 3. It's not a big number, right? So the greatest common divisor is a divisor, so it's a small number, but it's the biggest one in the list. It's a 3. Notice there's always going to be a common divisor. What for sure will divide any two numbers? Guaranteed, hands down, no questions asked. 1. So there's always a common divisor. It just may be the number 1 if they don't have anything else in common. Okay, so can you see how this is a very nice list? It works with this sort of divisibilities ideas that we've been working with in the previous sections. If the numbers are small, it works really well with what students know from divisibility facts, just like flashcard kind of facts. It's great. But if the numbers get larger, it's not quite as helpful. Now let's take a look at one that's actually on the other end of the spectrum. So this is sort of like the lowest end of the spectrum of things that work, right? I've seen my daughter in elementary school. She's in 6th grade now, but I've seen her probably 4th grade bringing home divisibility that looks like this, where they list all the factors, they circle the common factors. So this is like the elementary side of things, okay? The next one is sort of the other end of the spectrum. This one moves the best into algebra, but it's the least connected to what we did in elementary school. So this is prime factorization method. So we construct the prime factorization of each number, which we've talked about, factor trees and the division algorithm. We choose all the prime factors that are common to each factorization. So we look for common factors again. Anything that's common to both gets included. We list each of those prime numbers with the smallest exponent in either of the set of number, either number we're working with. And then we find the product. In other words, we multiply it out. This works really well because it lends itself very nicely to variables. You can do stuff with this with variables that doesn't work near as well with that other method we were doing. So we're going to have bigger numbers when this method is presented to us to use. Oh, let me pause just a second. We still have a few people writing. So 400 and 360. I would say I don't know about you, but I do know about you. You do not want to write down all the factors for 400. I know you don't, right? It means a large enough number that writing all the factors that divide 400 down would be annoying. Yes? And 360 equally annoying. So that previous method that we used, it would work. Okay, does everybody get that? Like, it will work. If you wanted to do it that way, you could do it. But it's going to take you probably more time than you really want to spend. This method cuts that time down when the numbers are bigger. So I'm going to do it with a division algorithm that I did last time, or maybe a couple times ago. I think it was last time. And we're going to start with 400, and we're simply going to divide by the smallest value that divides 400. Not 1, but bigger than 1. So what's the smallest prime number that divides 400? Don't overthink this. 2. Yep, 2. So 400 divided by 2 is 200. And we go again. Can I do 2 again? Yep. And I get 100. Can I do 2 again? Yes. And I get 50. Can I do 2 again? Yes. And I get 25. Can I do 2 again? No. What's the next prime number after 2? It would be 3. Will 3 divide 25? No. What's the next prime number after 3? 5. Will 5 divide 25? Yes. And it will give me a 5 at the end, which is prime. So I have all my prime factors there along the left. So this is 2. How many 2's are there? 4. And how many 5's are there? 2. So the prime factorization for 400 is 2 to the 4th times 5 squared. We're going to do the same thing with 360. Smallest prime number that divides 360? 2, which gives you 180, which divides by 2, which gives you 90, which will also divide by 2, giving you 45. So 45 is one of those numbers that as you look at it, you probably know some things that divide it, like 5, but we still are trying to go in order. That's the idea. So it doesn't divide by 2, but does it divide by 3? It does. How to remember, or remember with me, how do we know that it divides by 3? What's the rule? Add them up. So what's 4 plus 5? 9. Does that divide by 3? Then 45 will as well. So what is 45 divided by 3? It's 15. Will that also divide by 3? Yes, it will, leaving me with 5. Okay. Again, this method has a nice pattern and kind of ordering to it. You can see all the divisibility prime factors over there, in row. So I have how many 2's? I have 3. How many 3's? 2. And how many 5's? 1. So I'm not going to write 5 to the 1, but it's sort of understood that it's there, right? Okay. So what we have done so far is we have done number 1, and it's the lengthiest part of the process, okay? We have constructed the prime factorization for each number. Not the only way to do it, but that's why we did it. Second thing says we're going to choose all the prime factors that are in common. So what prime factors do these two numbers share? 2. Hold off on that. Just 2 is a prime factor and 5, okay? That's the next step. They have bases that match, right? The prime factors are 2 and 5. So that's step 2. So we've done 1 and 2. 3 says that we're going to use the smallest exponent that base has for any number. So in this one, the number 2 is 2 to the 4th in 400, and it's 2 cubed in 360. We use the smaller of them, so we will use the 3. So this is 2 cubed. The one on the left has 5 squared. The one on the right has 5 to the 1st. So we will have 5 to the 1st. Okay, that's step 3. Common bases, smallest factor. Okay, smallest exponent, I should say. And then the last thing then is to find the product, which simply means I need to multiply those values back together. Okay, I broke them all down and divided. Now I'm going to multiply them back up together for the answer. So do you know what 2 cubed is? 8. And of course, 5 to the 1st is 5. What's 8 times 5? 40. How could we check to make sure that at the very least this is a factor of both of them? We could divide, right? And you can use your calculator if you wish, right? You can take 400 and you divide it by 40. You can take 360 and you can divide it by 40. That does not guarantee that it's the biggest one, but at the very least it guarantees that it is one. Okay, so there's a believability, a reasonableness to our answer. Okay, any questions on that one? Okay, strategy number 3, and I will tell you this next one is my favorite one. I like this one a lot. This is division by primes. The division by primes looks a little bit like the one that we just did, but it's a little quicker. That's always good. So we write the numbers that we're dividing in a row, like just side by side. We divide them by a common prime factor. And then we repeat that. We divide what we just got there by another common prime factor, and we keep repeating until no other common factors can be found. And then much like on the last one, we multiply them back together. So jot all that down. I'm going to go a little off script on the next one and change the question that's actually in your notes. So if you have your notes already printed out, I'm going to go backwards, and I just want this to say 400 and 360. And the reason is because I want you to see how it looks different than the last one we did and how it looks the same. So you can see kind of a comparison a little bit better. So let's go with 400 and 360. And the first thing it said was to write them in a row. Here's our row. It's not a very exciting thing to do. And the first thing we do is we look at what divides them. Smallest, it's still smallest primes, okay? So it's division by primes. That's our method, right? So we better be dividing by primes if we're actually using that method. What is the smallest prime that divides both of them? 2. 400 divided by 2 is 200, and 360 divided by 2 is 180. Does that feel like what we kind of just did? Yep, it does. And we're going to keep going. What's the next smallest prime factor that divides them both? Still another 2, which gives me a 100 and a 90. What's the next smallest prime factor that divides them both? 2. And I get a 50 and a 45. Okay, so 2 is no longer going to divide both of them, right? Y'all with me? So what that means is that I simply don't divide anything else by 2. No more dividing by 2 is going to happen. So we're going to go to the next prime number, which would be 3. Will 3 divide both those numbers? It will not. So we go to the next prime number, 5. Will 5 divide both of these numbers? Yes. 5 gives me 10. 50 divided by 5 is 10. And 45 divided by 5 would be 9. At this point, 10 and 9 have nothing else but the number 1 that divides them, correct? So we would call 10 and 9 relatively prime. Compared to one another, they have nothing that divides them, and we would stop. So here's the cool thing. We did less division, and we got the same answer that we did in that other method, right? And our answer is all right here and needs to be multiplied. So our value for our greatest common divisor is 2 times 2 times 5. Which of course is still 40, just like it was before. But there's just a little less work involved. I don't have to get the entire prime factorization to find this value, right? You've probably had other instances in your life where you've done more than was necessary and you're like, okay, great, I did a whole bunch of extra work, right? I could have stopped at this point, but I wasn't thinking and I just kept going. That's the deal. I mean, this is like, that allows us to make a stopping spot where we find exactly how much we need and nothing more. I like division by primes a lot. Okay, so this is method 3. There's one more. Y'all ready for it? We will come back to both prime factorization, well, the list, one we did before, the prime factorization, and this one right here, the division by primes when we do least common multiple. You can use all 3 of these methods and also find least common multiple with the same information. So they're very versatile. The next one, not nearly as versatile, and it's a little bit more, not a little bit more, it's much more hidden as to what's going on. So this is called the Euclidean algorithm. And it's not that hard to do, but it's weird to write down. It's like our divisibility property for 11s. It's weird to write down. Okay, so here's the process. We're going to divide the larger number by the smaller one. And after we do that, we're going to find, that it comes out and it's got a remainder and all that kind of stuff, right? You're going to divide the previous divisor by the remainder. And you're going to repeat that process, the previous divisor by the remainder, the previous divisor by the remainder, until we get down to a remainder of 0. And once we do that, the last number that we divided by, the last divisor, is the greatest common divisor. You said it's actually not hard to do. You'll see it. But it's odd, and it feels sort of funny, and it's weird to write down. This is also the one that tends to trip people up the most. So we're going to do this with our 400 and our 360 first, and then we'll do it with the example that's actually listed, just so that you can see that you're going to get the same answer of 40 in this strategy as well. Okay, so while I understand that this problem says 72 and 126, let's do 400 and 360 first, okay? So what we're going to do is we're going to divide the bigger number, 400, by the smaller one, 360. Fabulous. How many times does 360 go into 400? Don't go overthinking this. Once, you bet. 1 times 360 is 360, and if I subtract, I get 40. Everybody good so far? Okay, what it said then is that I take the previous divisor and the remainder. So the previous number I divided by, I've only divided by one number, is 360, and the remainder is 40. I take these two numbers, okay? And the 360, which was previously outside of the division, is now going to be under the division. So the 360 moves underneath, and the remainder moves to the outside. Okay, 360 underneath, because it previously divided by, and now it's going to be itself divided, and it's divided by the remainder. How many 40s are there in 360? And you can let your calculator tell you. It's 9. And 9 times 40 is actually 360. Which gives me a remainder of 0. The remainder of 0 tells me to stop. And the answer is the last number I divided by. And that was pretty quick. Awkward, but it was quick. I got to the answer faster than any other way I did it. Okay. Now let's actually try the example we're supposed to be working on and see how it works with another set of numbers. Okay. So we take the biggest number, 126, divided by the smaller number, 72. So how many 72s are there in 126? 1. Okay, so 1 times 72 is 72, and if we subtract, what do we get? 50, I think it's 54. 54. Okay, 54. Okay, so these are the two numbers of consequence, right? The number that's on the outside of the division and the remainder. And it's always big divided by small. I mean, really, you just look at it and you'll know. Well, the big one's the 72, so that's going to go underneath the division bar. Smaller one's the 54, so it goes on the outside. How many 54s are there in 72? 1. 1 times 54 is 54. And if I subtract, I get 18. So again, these are the two numbers that matter, the remainder and the divisor. Bigger number underneath, that's the 54. Smaller on the outside is 18. How many 18s are there in 54? It's 3. Yeah, somebody said 3. What's 3 times 18? It's 54, yeah. That 0 remainder tells me to stop. What's my answer? 18. The answer is always the last thing we divided by. So my GCD is 18. Okay? Technically speaking, it's not terribly challenging. It's not a very difficult task, and especially because you're using your calculator to do all the divisions, right? You're like, how many whole number times does it go in and all that good stuff. But it's definitely veiled, right? This is not very clear as to why or how it's working. This one is. I can see exactly why this worked. It's very obvious how I'm doing the division, why the values actually worked out each of the times, and how I'm multiplying them back together. And to be honest, the same's true about this one and this one. I can see better why they're working. Okay, so we're going to stop there today.